the coursework?
I don't know, do we?
Well, I mean,
No, it's
Well,
recording.
right.
I don't think there's anything secret.
You'll try to mark it as soon as possible?
Yeah, right. Yeah, as soon as possible,
And
which
then
is not saying much.
you'll communicate the results of this process somehow by pushing if you can,
Right,
emailing if you can't.
yes.
Yeah, so expect to get your marks back as soon as possible.
It's a bit tricky.
If I promise end of this week, is that too much?
The end of this week?
Yeah.
Yeah, it's too much. It's way too much.
Next week?
As I said, there's lots of grant application deadlines, so yeah, I'm having a lot of meetings at the moment.
Okay, okay.
We should aim for 2 weeks, but you know,
Yeah.
aim is the. Yeah.
Okay, fair enough. Anything else to announce?
I don't think so.
Okay, so let's continue today with what we did last week, which was this little expression language, which so far contains natural number literals, Boolean literals, additions of things, and if then else. Right? And last week we went from this nice and cheerful, but clearly not very type-safe, untyped language, where we could add any two expressions. And then we realized when we did the evaluation of these things that didn't work. So we had to say that we could only maybe produce a value, to the type version where we actually made sure that we're only adding things of type not, and that produces something of type not. Right? And then we had this erasure function, which took a high information thing, a typed expression, and returned the corresponding low information thing. So it's turning nuts to nuts, booleans to booleans, additions to addition, and if then else to if then else, right? Just working structurally. And we said that, okay, this looks like it's doing the right thing, but how do we actually prove that it's doing the right thing? So we said that, well, if we have a typed value, so these were just values, but we made sure to index them by the type. So we said that, well, if your expression is of type bool, then the value is really a boolean, and if the expression is of type not, then the value is really a natural number. So if we have a typed value, then we can always produce an untyped value, again by sending booleans to booleans and natural numbers to natural numbers. Right? And then the last thing we did last week was we formulated this correctness property, which claims that if you take a type expression, so you start with as much information as possible, then there's two things you can do with it. You could either just evaluate it as a typed expression, that's going to give you a typed value, so then you can embed that typed value, that gives you a value, and then you can compare that with what happens if you first forget about the types, so you erase the types, and then you evaluate it as an ordinary expression, right? So, and the claim is that these two things are the same. It doesn't matter if we first erase and then evaluate, or if we evaluate and then kind of embed. But we have to put this just here as well, because we're claiming that we're always producing a value in this case, right? So this eval function sometimes produces nothing, but the claim is that if you start from a typed expression, then you will always get a just. And not only will you always get a just, you will get a just of the same value that you get if you evaluate it in the type way. Right? So this is one way to say that this erasure function is really doing the same thing. We get the same value no matter if we erase or not. Right? Okay, so let's see if we can actually try to prove this. So how would you do it? Well, all these things here are really doing just pattern matching on the expression, right? So we can see it here, and if I go to the definition of t-eval, it's also doing pattern matching of the expression. And eval is doing pattern matching on the expression, except here we have this slightly more complicated do block in the middle. So we need to worry about that eventually. But our first move is surely going to be to pattern match on E to see what it is, right? So I'll do that.
Yeah, so remember that the slogan when you're proving an equation is what is it stuck on, And here we can see that it's all stuck on E, so it's the natural move to match on E rather than the type, for instance, which wouldn't give you anything.
Okay, so I'll just rename them the way we normally do, or some variation of it. And then we also have to look at these cases, right? So let's deal with the base cases first. If they are not easy, then something is really wrong. So we see that in this case, my goal has become just not n equals just not n, right? Because the t eval of not n is just not n, the embed of not n is not n, so that's why the right-hand side is just not n, and the left-hand side, well, the erasure of not n is not n, and the valuation of not n is not n. Right? So, of course, I don't need to know that. I can just type reference and be happy. And the same thing here. I expect it to be easy. Okay, and then here for addition, it looks really complicated, right? So what's going on here? Well, in the definition of eval, we used do notation, and whenever you use do notation, that's desugared to these uses of bind internally, right? That's why the bind is coming here. And then here, we also have a pattern matching lambda because we had this where expression here. Sorry, this where expression.
Yeah.
And here we use the catch-all, but that catch-all has been expanded to all possible values here. So we said, well, if it's a not
No, that's the next one, I think. The catch-all is here at the bottom because of the nesting. At the bottom of the goal.
Ah.
Yeah.
Ah, I see. Yes, you're right. Right, so here, there's three patterns here, right? Either we have the happy path, not n prime, that corresponds to this pattern, where we move on and return this, or we have the two unhappy paths, both true and both false, where we return nothing. Right. Okay, so it looks a bit messy, but the thing that this thing here is really stuck on is this first expression, eval E, right? Because if we look at the definition of bind, or imagine what the definition of bind is, we can look at it if I can get to the top of the screen. Well, we see that the bind, if the first thing is nothing, then the whole thing is nothing. If the first thing is a just, then we continue with the continuation f, right? F of the underlying thing. So the reason that this thing here is stuck is because we don't know if this eval of this is a just or a nothing yet. Right? Okay. But actually, I know that this thing is a just, right? Because the E that I have, the E that I have is smaller than the thing I'm looking at, so I should be entitled to an induction hypothesis which says that exactly evaluating this erasure is going to be a just of these things, right? So I should know by the induction hypothesis, I'll do this applied to E, and look at the bottom here, then I know that that thing is actually a just. So in this case, I think it's a good idea to kind of pattern match on this additional fact, right? So I'm going to say with this, let's see what happens. Okay, then I have to add my new case. So I say with the expression I want to pattern match on, I say dot 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 to repeat everything on the previous line, and I have one extra pattern which I normally call QQ because I know I want to pattern match it on it very soon, so this name is not going to survive anyway, right? So we see that now I have this extra pattern QQ, which tells me something interesting about the erasure of E. Right? So if I pattern match on that QQ, then this often happens. So what is going on here is that I have an equation between two terms. And when you pattern match on a proof of an equation, then what Agda is going to do is it wants to replace the left-hand side with the right-hand side, right? But that only really works if the left-hand side is a variable where you can replace it. So I need to make sure that this thing is a variable. And the standard trick to do this is to do a with on that thing, kind of before you do a with on the equation you really want. So now EE, QQ. And now if we look again, we see that that expression has been generalized in the goal. And in the type of QQ, the left-hand side is now a variable, right? So I can have better hope of actually pattern matching on QQ. Okay, so now Raffle was the only possible inhabitant, but that doesn't look like it did much. But now, well, I still have another goal, but we see that the eval E, the EE has disappeared now, right? That turned into a just, so then turn this back into an R. We see that we are now moved on into this case where this thing really was an atom. So we made some progress. Okay, but now I have the same problem with the E prime, right? So I'm going to do the same thing. Do a with eval E prime and the correctness of E prime. And now I think I will get bitten by multiple dots, yes. So maybe Guillaume has a clever way to do this?
No, I think you don't need to add the first ones.
Okay, let's just try it like this. Yeah, so I never know how to do this. What I do if I have nested widths, then I'm just expanding the first dot.
Oh, is it not that you need to also list EE and Raffle? I can't remember.
So this is what the dot means, right? Repeat the line above, and I never know how to deal with the nested widths. Probably some way to do it, but if life is too short for that, then you can always just expand it by hand. Right? Because now we are here, we have abstracted eval of E prime to EE, and we have QQ again, which tells us what EE is, so let's pattern match on QQ. Okay, then this time, right, it actually expanded it, fine. The dot here means that this pattern has been fully determined by other things. If you think that's too noisy, you can always replace it with an underscore, for example. Okay, and now finally we are in a good place, right? So you can just say Raffle at this point. But it's only possible because we did two recursive calls here, right? So we kind of rewrote the eval of the erasure of E and the eval of the erasure of E prime. And then it worked out. So okay, let's see if we can do this one as well. So it looks like a similar thing, right? The first thing we're doing here on the left is we are evaluating the condition, EB. So let's follow the same pattern.
So I think in this case you can maybe try to use rewrite for pipe correct.
Okay. So this is a very common pattern, right? Where you have some equality expression and you abstract on the left-hand side of it, so you get a variable to rewrite. So Agda has special support for this, which is saying just rewrite by the correctness of EB. So what this is going to do is it's going to abstract on the left-hand side, it's going to do a with on the thing you put here, and it's going to match it against Raffle. Right? Which is kind of what we did by hand. Did it work?
Right, it did, but in that case it was a terrible idea because now we actually want to inspect the value that was generated. So it was a better idea in the add case, I guess.
Yeah, okay, so let's go back to...
So rewrite allows you to deploy the equation, but because you're not abstracting over the left-hand side, there's no way for you to make additional observations of what the left-hand side is shaped like. So if you just need to deploy the equation once, that's fine. But here, to actually know which branch of the F then else we've picked, we are forced to pattern match further on the result.
Okay, so now I can pattern match on Q. Then kind of back in the same place, but I want to know what this is, right? So I'm going to pattern match on EEB as well. Okay, and then I'm not allowed to do that because it's actually this thing. So actually what I want to pattern match on is, well maybe I want to actually abstract this first. Is that a good plan, you think?
With over T eval, yeah.
Because what I really want is to know what this thing is, right?
Right.
So do I dare to do it here? Okay, and then this is good.
Oh, it should work, I think.
Let's move up again.
Okay.
Okay, so that looks good. So now my expression has been replaced by this variable, right? So I should now be able to pattern match on that variable. Okay. And then everything has simplified nicely. This now looks like just a recursive call on EE. Here it looks like a recursive call on ET. Right. Okay, so it takes some practice and some confusion before you get used to these things, right? But basically, we are following the same pattern of pattern matching as in the definitions, and then we are deploying the right kind of widths to make things compute. And this last one was a little bit maybe even more confusing because we saw that we had an expression which had this thing on both sides and we wanted that to compute, and that's what made us unstuck here. Right?
Should we show what happens if you're doing two widths instead of with eval and pipe correct?
Right, you mean here, for example?
Yeah.
Okay, let's just comment all of this out for now. Okay, so you're saying, let's do it here, right? Okay, so you want to do a width on the correctness of this thing. Right, so now I have my Q and I can pattern match on my Q. Well, I can't. Why is that? It's because if we look at the type of Q versus the goal, so Q is still talking about E prime, right? But the goal is talking about this new variable we introduced to stand for the evaluation of E prime. So by splitting this up into two different widths, we've lost the connection between E prime and the evaluation of E prime. So when we then later do another WID, Agda has forgotten about the fact that this was supposed to stand for that, right? Because it's at the point of doing the WID that we're generalizing over the goal and so on. So that's why it's important to do these two in parallel, like this. Rather than the other way around.
So that we're abstracting over not only the expression, but also all of the useful properties that involve that expression. Otherwise, we lose the connection to that expression and we can never recover it.
Yeah. So it takes a little bit, takes some time to get used to this, but eventually you kind of know what moves to make, and you can't really mess up, right? I mean, the worst thing is Agda tells you off, and then you try something else. Okay, so that's how you can prove correctness.
Well,
so
yeah, stay on this one, and then I can suggest something else. Yeah.
Okay.
So we showed you one direction, and if you're starting from the more typed version of the language, evaluation is the same as if you erase back to the less typed and then evaluate there. But you might want to see whether something different is provable. So for instance, could you prove something going in the other direction, right? So this is talking about a really well-typed thing. Could you prove that for any expression E, if the eval of E is just a value, so here V a value, let's call it co-correct so that it doesn't clash, then there exists an E prime such that the erasure of E prime is equal to E and embed T eval E prime is equal to V. As this, we don't have the existentials. And we don't have time. And we don't have times.
You need to change one of the primes.
Right, cheers. Up. Oh, I guess you need to say that there exists a type also. Oh, exist a lambda type such that tx per type. Okay, so now we don't have any yellow left. So if you look at this thing, right, it's saying that all of the typed expressions can also be seen as untyped expressions, and they have the same value. And the question is whether you can go in the other direction. All of the well-behaved expressions, so the ones that compute to a value, do they have a type such that there's a typed expression that corresponds to them and they still have the same value? So just to show that we gave you the right version, like the easy version, if you try to prove this, if you think a little bit about the way we designed our type system, you should see that this is probably not provable, because you can have different branches of an if-then else, all of which are computing to a proper value, but have different types. And then the if-then else, because it constrains the two branches to have the same type, will prevent you from building such an expression. And this is actually quite common when you have type systems. It's that they carve out a safe subset of terms, so terms that are well behaved, that are guaranteed to give you a value every time, but they also do not capture all of the well behaved terms. So there's a bit of a balance between giving you safety, but also not giving you everything. And of course, type systems like Agda's and others give you more and more expressivity to try to capture more and more of the set of terms that are safe. In Agda, for instance, the fact that two branches of an if then else have different types is not a big deal because you can have dependent types. But maybe there are other terms that are well behaved and that we cannot capture. So it's always a good idea to keep in mind like this sort of potential limitations of your type system. Okay. So
one very quick comment is that there exists a type expression such that iteration is E. This is exactly how I define the kind of well-typed predicate, right?
oh yeah, that's true. Actually, I could have. Yeah.
So it's not a coincidence that these things come up over and over again, right? Because they are concepts that make sense for these things. But yeah. Okay, let's move on.
Right. Yeah. So the other thing I wanted to show you is so this is the inference we had the other day, where we were, well, for the atoms, we're willing to conclude immediately because they have an obvious type and they have a type version and then they erase the right way. And then for the compound expressions where you have like a top node and then substructures, we're doing recursive calls saying, well, if I have an addition, I'm going to infer that the left branch has a type, and then I'm going to check that this type is not, and then I'm going to infer that the right branch has a type, and then check that the type is not, and then I can come to a conclusion that these things are the way they are. But you can actually restructure this code a little bit. So this is something I pushed last week, but maybe you haven't had a look at. So when we're looking at the addition nodes, we already knew what type we wanted, but we still went through the whole like dance of inferring first and then checking and so on, checking for equality of the results and what between the result and what we expected. Turns out we can do a bit better, and we can actually have sort of what we call a bidirectional approach. So infer, if you think about the way it processes the tree, right? It's getting information from the leaves, where you know that the nat literals and the bool literals are respectively of type nat and bool, and then it propagates the information upwards. So if you have the if then else, you look at the type of each branch, make sure they're equal, and then you're pushing out the type of the overall expression. But we could also go in the other direction. We could know what we want already. So if we have an addition node, we know that we want the left and right branches to have type nat. So we could instead be pushing the types into it. And so this is what this, I guess I have a different type of well type now. So well type now is giving you the type that you want and the row expression with no type annotations. And this row expression is well typed at that type precisely whenever there is a typed expression of the appropriate type together with a proof that if you erase it, you get back the original term. And then you can split your definition into two mutually defined functions. One that will take an arbitrary expression and then try to come up with a type. So this is the existential, which is encoded just with a dependent pair. So it's saying maybe there exists a type such that E is well typed at that type. And check is going in the other direction. So it might still fail because your expression can still not be well typed, but it's not trying to come up with the type this time. It's given to this function, and it's telling, well, I will make sure that if I return a result, it will be exactly of that type you gave me as an argument. And then the way you...
Can I suggest we rename well type to is of type or something?
Oh, sure. Yeah, okay. I was trying to see whether I could have like a cute notation, infix, and like something meaningful, but
Insertion replaces your friend here?
yeah, there's not that many of them.
Except the constructor is badly named now.
Oh, I see. Fair. All right.
Because this really is the relation saying that, well, the expression E is of type tie, right?
Yeah. Yeah, I'm putting the type first because in my mind it comes first, and then it's a constraint on the shape of the term, rather than arising from the term, which is when we sort of reverse this direction here. And then if you look at the code, well, when we have literals, we can infer the types just fine. But when we have an addition, we check the branches rather than inferring and then checking for equality. So we're a bit more explicit in our strategy. And then we can just put it together, just like we did before, except that now we don't need to check the results for equality because we know statically that if we get a result here, it's guaranteed to be the right NAT-shaped thing. And then in the if then else, it's similar. So we know that the scrutiny of the if then else needs to be a Boolean because that's what we branch over. But then we have two branches, and in the infer mode, we don't really know what they are. So we infer the first one, and then instead of, which gives us a type and a term, and instead of inferring the second one and then making sure that they have the same types, we just check it at that type. And then for ease of implementation, I just said that checking is exactly the pattern that we had of inferring and then checking for equality. But that pattern has been isolated in a mutually defined function to clarify our goals. Okay. Right.
But you could imagine writing this again, pattern matching on E, right? And then you wouldn't have to write this equality check for types.
Yes. And then in the if then else case, you wouldn't need to infer the types of the branches anymore because you would be pushing the type from the outside, and you know that the two branches need to have exactly the same type as the overall expression, so you could just propagate that information down. Which in this language it doesn't really matter, but in other languages where it's not always possible to infer all of the types, actually adhering to that strategy of pushing all of the information that you have as much as possible can help you type a lot more terms than if you're trying to come up with the types yourself. Okay, so before doing optimizations, we thought we would make the language a bit more interesting. So go back to the beginning, and we wanted to, okay, that's going to be, should I make expert well scoped or?
Yes, but should we just work with the well-type version? We can forget about that.
Oh yeah, okay, we can, yeah.
Make a copy of it rather than modifying it, right?
Right. Let's just move to a different file because it's going to be annoying.
Because it's week 6 now anyway.
The erasure is not going to, oh yeah. Right. All right, so hopefully this will not take too long to set up. Right, so all right, and we have a new pound, or do we actually? Maybe not. Right, so what we wanted to do, because here all the expressions are static, right? If you have an if then else, you know that if you evaluate this enough, you will actually get a value at some point, which means it will be an actual Boolean, a true or a false, and then you will be able to reduce the if then else, and eventually any expression computes to either a natural number or a Boolean. But in practice, you might have, when you're writing a compiler, you will have programs that are not fully known at compile time, otherwise you would never need to run them. You could always return the exact value constantly. And to model that, we just need to throw in variables. So variables are standing for unknowns. In your typical program, they would arise from doing I/O basically. So any kind of effect where you don't know what the value is because it will be determined at runtime sort of blocks the overall execution. And that's why in the grand scheme of things, you cannot always compile a program to a single like constant value. So okay, to add these variables, well, we have a language of typed expressions here. So I guess one thing we could do, but that's kind of boring, is just say I have a single variable. So I could say this is var as this type, and then I have an expression with an overall type. And okay, maybe I should do search and replace. Oop. Can I?
And also can you call var type rather than
Yes, okay. Took. This is hopefully.
because that's what this is supposed to be, right? The type of the variable.
So now my lines are really long, so I'm starting to reflow things. Okay. And if you remember, what mode did I enter? That's bad. Okay. So now I'm shaping this like usual logic rules, right? Saying you can prove T if you can prove bool T and T. This is a fairly boring proof, but a rather interesting program. Okay, so now we have this new language where we said, well, there's just one variable in scope. It has type var_ty, and we have all our usual constructors. They do not modify the context, so the variable is still the same. But we can throw in an extra constructor, so hold same, that is giving us an arbitrary var_ty expression. So this new symbol is telling us that, well, it's standing for the one variable that we have, and it has type var_ty because this is what we said our type was, or type of the one variable was. But this is still kind of boring, so we can do a little bit better, and we can import lists. And then we can say, well, you can actually have as many variables as you want. If I can type this, yes. So now I'm gonna change var_ty into comma, and this is a list of type. Okay, so that doesn't type check, but that's good. So now this is saying, in this context where you have, however long the list is, many variables, each of which has its own type associated to that position in the list, I can say that the overall expression has type ty. And of course, all of these keep working because they were sort of, beforehand, they were working morely in the empty context. Then we added one variable. They were working in a context with just one variable. And now they're working in an arbitrary context with arbitrarily many variables. The only important thing is that it's still the case that in if then else, for instance, all of the branches have access to the same context. Otherwise, it would be a bit weird, right? If the left branch had access to somehow more variables than the right one. But for this one constructor, our naive approach doesn't work anymore. So what we want to write instead is something like this. We can, for some type sigma, we'll have an expression. Things are just disappearing. We'll have an expression, a typed expression of type sigma in context gamma. But we need to somehow tie this sigma to the existing gamma. Like, let's say we have an empty context, then it doesn't actually make sense to talk about one of the variables in this context, because we actually need to be referring to something that exists. Or if we have a context with just variables corresponding to natural numbers, it doesn't make sense to say, well, I can use a var to create a Boolean. So the way we do that is we say, well, sigma better be somewhere in gamma. So the typical notation for this is the belongs or the LM symbol. And then how do we define belonging? Well, it's just an inductive definition. Well, just, okay. So for any set A, we can define what it means for a value little a to be somewhere in a list. But so little a is a parameter because we're talking about a specific one. We're going to say where it is in some arbitrary list. But the list cannot be a parameter because it will vary throughout the constructors. Let's see. Well, it's
be clear when you do it.
Yeah. So, for instance, it doesn't make sense to have little a somewhere in the empty list, right? Because then you can just create anything you want. So we won't have such a constructor. And that's why also we cannot just have a constant, like a variable x's list of a that would show up somewhere here, because in particular you could pick x's to be the empty list, and then you would have a constructor that is just meaningless. So the two ones we like to have, well, they can have different names, but we can say that either the variable we're looking for or the element actually it's not limited to variables in this definition, is here, and we say that it's here when it's immediately available at the head of the list. So A is in something. Does that work? No, that probably doesn't work. Oop.
You need brackets around the const.
There we go.
Can you still put some brackets in the
Sure, I can put some brackets. So here we're saying that A matches exactly the head of the list, and therefore it belongs to the list, right? Note that this is fairly restrictive. You could relax this a little bit by making it modulo like a notion of being related to the value, but here we're just going for equality. Or it could be a bit further away over there. So if we have a list and we know that A is in it, then it is also in, this is again not going to work, right? Yeah. In the list extended with another value that we don't care about. So here we only care about A being somewhere in the list. We don't care about A being the first, we don't care about finding the first occurrence of A in the list. So this is why we can use this constructor, and we don't actually care what X is. If you wanted to formalize what it means to be the first one, you could, for instance, add something like, if X were equal to A, it would be absurd. And then this would give you a different notion of belonging where you're actually finding the first such value. But of course, in a programming language, you can have multiple variables of type bool, and they're actually different, right? They are standing for they're building, referring to one or the other, will build different programs that will potentially have different values at runtime. So we do want to be able to refer to not just the first variable of type bool in context, but any variable of type bool in context. Okay. So now we have this expression, this typed expression language. Do you want to write an evaluation function for it?
Yeah, we don't have that much time left, so maybe we
But
should just give some examples.
But the evaluation function is copy-pasted except for the first case,
Yeah, okay.
right? So,
Okay, so I'm going to take this. How do I turn off my Frenchness?
oh, sorry. There we go.
Thank you. So I'm going to take the old evaluation function we had, paste it in, and then I need to change the type of it because our expressions now have this context, which we normally call gamma, right? I guess I also need to copy in the values. Okay. And I need to do the right kind of import.
Right. It's never just copy-pasting.
Else. Okay, so now I'm told that I haven't dealt with the variable case, which is fair enough because I haven't dealt with the variable case, right? So I'm going to see what I need to do. So here I have a variable. X is a proof that the type T occurs somewhere in my list gamma, and I have to give a value of type T out, right? But if I think about this, what should be the value of this variable? Well, I don't really know, right? This is maybe the second variable in my context. So this X kind of tells me which variable it is, right? If it's here, then it's the first variable. If it's there over here, it's the second, and so on. But I don't have any values associated to these things. So I also need to change the evaluation function to basically I need to be told what the values of the variable should be, right? I can't tell you what the value of X is unless I've given an environment that tells me what the values of all the variables are. Right? So I guess I should import something more, because what I would like to say...
Or could you define it as a function?
Yeah, okay.
Yeah.
So I could say that an environment for gamma, I guess I better give this a type. So if I have a list of A in general, A is a set, then an environment for a list of A, well, this should tell me for every element that occurs in this gamma what its value is, right? Okay, so maybe I just do it for types. I have a list of types. Gamma, well, then I could say that for every X, which is a type, if X occurs in gamma, then I want the typed value of type T.
Type X.
Of type X. Yeah. So for every type that occurs in gamma, I want a value for that type, right? So then here I could say my T eval should take an environment for gamma, and then for every expression it's going to give me a value. So So just by convention, we often call these environments row. So I guess I'm going to do that here as well. So everywhere I take this environment, and in the recursive calls, I just pass done. Okay, and then here now, I have my x, which is a proof that t is in gamma. So I should be able to use my environment on t, except that's not in scope. So I'm going to bring it into scope. It's implicit, but now I made it explicit. So row of t says, if you give me a proof that t is in gamma, then I'm going to give you a value. Well, I have a proof of that, great. So I'm looking up this particular variable in my environment, because my environment has a value for every type in the list, right? And it has the right, it's a value of the right type, x as well. Right? So my environment could say, okay, the first element is going to be sent to the value 5, which is a natural number. The second element is going to send to be true, which is a Boolean. The third is to 17 and so on. And here I'm just looking up the right value, right? But notice that if, do we have time for this? Not really. Let's notice things next tomorrow instead.
Right.
So if the list is empty, then it's no big deal to produce an environment for it, right? So we kind of really have generalized the previous case. Haven't done the previous case any harder in a way. Let's do that tomorrow.
Yep.
Right. I can't turn off the recording.
Yep.